Alright, so we're going to look at a couple more examples that we didn't have time to do in class of using triple integrals. Alright, so in this example, we want to use a triple integral to find the volume of our surface z equals 36 minus x squared minus y squared above the xy plane. And we know how to use a double integral to evaluate this, to do this. I just want to show an example of setting this up. And I mentioned at the end of class that right now we're using, when we're finding volume, we're using a triple integral to do what we did with double integrals. And a triple integral after the first integral turns into a double integral that looks like what we did in the last couple of sections. We have to use triple integrals if we want to find centers of mass and moments of inertia of a solid versus a planar lamina. So that's one reason why we would use triple integrals. And we're going to end up using triple integrals for other things than finding volume and finding centers of mass and moments of inertia. So part of what we're doing is just building our toolkit and developing the techniques of setting up triple integrals so that when we're applying them to other things that we have familiarity with them. So anyway, here's our surface. So let me draw a quick sketch of what we're talking about. So there are our axes. And z equals 36 minus x squared minus y squared is this paraboloid. So I'm going to draw it in the first octant. So there's our surface. And our boundary in the xy plane when z equals 0 is just x squared plus y squared equals 36. So we have the circle with a radius of 6. So that's our boundary in the xy plane. So our volume, this one's an easy one to set up. I'm just going to do the first octant and multiply by 4. So we get 4. X is going to vary from 0 to 6. Y is going to vary from 0 to the square root of 36 minus x squared. And z is going to vary from 0 to our surface, 36 minus x squared minus y squared. And we have the z, dy, dx. So after we do this first integral, the z integral just evaluates. This is constant with respect to z. So we just end up with the volume equaling 0 to 6, a double integral like we were doing before, 36 minus x squared of 36 minus x squared minus y squared dy dx. And because our boundary in the xy plane is a circle, it's going to be much easier with polar coordinates. And the switch to polar coordinates is not difficult. Our volume is going to be, and I forgot my 4 here, 4 times the integral from 0 to pi over 2 in the xy plane. Our radius varies from 0 to 6. Our function that we're integrating becomes 36 minus r squared. And our polar area element are dr d theta. Nice, easy integral to evaluate. And this evaluates out to 648 pi cubic units. This much easier to evaluate than this, especially with this radical. All right, next I want to finish the example we started. We talked about the procedure for in class. So we want to find the centroid of this unit, region, or solid, I guess. I guess it wouldn't be the centroid. Well, it would be the centroid. We're talking about a uniform mass distribution, what I'll call a center mass. And we'll sketch our region again. So our region was just defined by some points, and we decided it's where the plane, our surface was a plane. The plane was intersecting the first octant here. So this was 500, 004, and 030. So to find we need an equation that represents our surface, and we decided we could use vectors, represent the sides between 2 points as a vector, and take the cross product of those vectors to get a normal vector to our plane, and use that to write the equation of the plane. So I'm going to call this, I'm going to draw an arrow here, and draw an arrow here, and I call this vector P and this vector Q. I'm going to use these two sides. So vector P is the vector -5, 0, 4, and vector Q is going to be 0, -3, 4. And we're going to take the cross product to find our normal vector. So let's form that cross product, P cross Q. -5, 0, 4. 0, -3, 4. When I do this cross product, I end up with the vector 12i plus 20j plus 15k. So that's our normal vector to our plane. That gives us our direction numbers. So our direction numbers are A equals 12, B equals 20, and C equals 15. And I'm going to use this 0.500 to write our equation, 500. We know that point is on the plane. We talked about that in class. So we know that that point's on our plane. So our equation is 12 times x minus 5 plus 20 times y minus 0 plus 15 times z minus 0 equals 0. And I need to rearrange that because I need to get my surface represented as z equals something. So if I distribute and rearrange, this rearranges to z equals 115 minus 12x minus 20y plus 60. So that's the equation of our surface, and now we can set up our integral. We will need our region in the xy plane though to get our x and y limits of integration. So in the xy plane I have the line, and this is y equals 3, and this is x equals 5, and I'm going to set my rectangles vertical. So I'm going to do dy dx as my order. The equation of this line using these 2 points, I get y equals minus 3/5 x plus 3. So now we can set up our integral. So I'm going to switch the page here, but we have our surface, we have our region in the xy plane, we set up our limits. So my integral, the mass, is going to be the integral x equals 0 to 5, the integral y equals 0 to minus 3/5 x plus 3, integral of z equals 0 to 1/15 up to our plane, 1/15 minus 12x minus 20y plus 60. And our density was constant. We said rho is a constant. dz, dy, dx. And we end up just integrating polynomials here. This is not a difficult integral to evaluate. I'm not going to go through the evaluation. The moment m sub yz is the integral over our region. Same limits for all of our integrals, so I'm not going to rewrite all the limits. Kx, dz, dy, dx. M sub xz, integral over our solid of ky, dz, dy, dx. And m sub xy is kz, dz, dy, dx. If I evaluate all of these, you should end up with mass equals 10 times our constant density, m sub yz is 25k over 2, m sub xz comes out to 15k over 2, m sub xy is 10k, and x bar 5/4, y bar is 3/4, and z bar is 1. And it's always a good idea to look back and make sure that this makes sense. So I'm going to look back at my surface, and if we're thinking of a center of mass, if we were to balance it at a point somewhere in the center there, our coordinates definitely make sense. All right, I want to look at one example of second moment of inertia. So we want to find our moments about the axes. So I sub x, I sub y, I sub z. Our density function here is k times 4 minus z. And our solid, we're going to start with a drawing again. So there's our solid region. We have the cylinder z equals 4 minus y squared is the upper portion. And this is at x equals 4. And this is at y equals 2. So we want to find the moments about the axes of this solid and with this density function. Now I mentioned in class that it's going to be easier, generally easier to calculate the moments about the planes and then add them to get the moments about the axes, because our moments about the axes involve x squared plus y squared plus z squared, etc., where the moments about the planes just involve the one term of that x squared or y squared or z squared. So that's what we're going to do here. We have a nice rectangular region in the YZ plane, or sorry, the XY plane. So our limits, our x and y limits are easy to set up, and our z limit is just defined by the surface. So our integrals are going to be nice to set up. So just get I sub xy equals the integral x equals 0 to 4, y equals 0 to 2, z equals 0 to 4 minus y squared, and our density function k, and we're about the xz plane. Our distance is z squared, 4 minus z dz dy dx. And I normally like to set up my integrals, my triple integrals, in the order dz dy dx. Just like double integrals, I like dy dx. It's just the order that I usually choose to set them up. So that's going to be our moment about the xy plane, or a second moment. Moment about the yz plane. Same limits. 0 to 4, 0 to 2, 0 to 4 minus y squared, kx squared, times 4 minus z, dz dy dx. And our moment about the, let's see, xy, yz, xz, 0 to 4, 0 to 2, 0 to 4 minus y squared, ky squared, 4 minus z, dz dy dx. Polynomials to evaluate these integrals, not difficult, maybe a little tedious, but not difficult. When we evaluate these, we end up with I sub xy, get some nice big numbers, is 32,768 k over 315. I sub yz is 4069 k over 15, and I sub xz is 1024k over 21. And then we can just sum these to get our moments about the axes. So I sub x is I sub xz plus I sub xy, and when I add those I get 48128 k over 315. I sub y, I'm going to add I sub xy plus I sub yz. And I get 118784K over 315. And finally, I sub z, I sub xz plus I sub yz. And when I sum those, I get 11264 K over 35.
Once you go use the computer in that, the door's open.
And in our next couple of lessons, we will talk about triple integrals in cylindrical coordinates and triple integrals in spherical coordinates, which will open up really a kind of a whole new world with triple integrals. Just using different coordinate systems allows the evaluation of integrals that would be really difficult otherwise. And then the last section that we'll talk about in chapter 14 has to do with transforming coordinates. If we have some boundary that is extremely difficult, sometimes we can do a transformation that makes our evaluation much easier.